Welcome to Chapter 5, Part 1, Energy and Thermodynamics. So in this section, we're going to talk about what is energy and what is thermodynamics. So the first thing we want to think about is the fact that energy, the study of energy and how it moves, is broadly called thermodynamics. And so we can see the word thermodynamics here. And so when we think about thermodynamics, it really is just the study of how energy is transferred or converted into work or heat. So by and large, we're going to talk about work and heat in this section. So energy is the capacity to do work or transfer heat. What does that really mean? So this means how much energy does it take us to move something, right? If you're going to move a heavy box, you might start sweating. And so that's a transfer of heat. And so you're going to do work or transfer heat. But when we think about that, we kind of want to think about what that means. So work here is going to be lowercase w, and energy, by the way, is capital E. Work is the energy used to cause an object to move against a force. So we can move something, you could pick it up, that is against gravity. And heat is the energy, which is a lowercase q, and it's the energy used to cause the temperature of an object to increase. So if we add heat, it will get hotter. If we take heat away, so if we add heat, we're going to say the temperature goes up. If we remove heat, the temperature goes down. Now, typically when we think about the temperature, we don't think about the fact that in the fall, we have removed heat from the environment. We think it is cooler. And so in this case, you can kind of think about removing heat as being something is getting colder, and adding heat, it will get hotter. And so we're going to talk about energy, work, and heat, but it's important to think about what the energy units are. And so energy units are in joules, which is a J, or calories, which is cal. So when we think about calories, we're more commonly associated, these are the, when we think about food, so if you eat a pack of goldfish, maybe it's a 100-calorie pack or something else, this calorie is related to that. And so joules is just the more scientific unit instead. So one of the other things we want to think about is there are two basic types of energy. Well, there are several. So we have kinetic and potential. So kinetic energy is E sub K, and that is 1/2 mv squared, where m is the mass in kilograms, and v is the velocity in meters per second. And so that is squared. And so kinetic energy, we often think about this when we think about a ball at the top of the hill. And so this is the energy of motion. And potential energy is the stored energy. And it turns out that calculating the potential energy is a significantly more involved calculation. And to be honest, we're not really going to calculate kinetic energy and potential energy in this course. They are important in chemistry, but when we start to think about kinetic versus potential, what we really want to think about is chemical energy. So typically we think about electrostatic energy, which can be annotated E sub EL. So E for energy, and EL is for electrostatic energy. And so electrostatic energy arises from the interaction of two charged particles. So when we think about that, if we have a positive charge and a negative charge, these two charges are going to be positively interacting. Now, hypothetically, if we also had a positive charge and a positive charge, instead of being attracted to one another, they are going to be repelled. And so I will annotate that with blue moving away. And so these charges want to interact with each other, and they do. And so this could be calculated using E sub EL is equal to K Q1 Q2 over D, where K is the proportionality constant. And the proportionality constant is, in fact, 8.99 times 10 to the 9. Whoa. My joules got a little messed up. Joules meters Coulomb squared. And so this value would be provided on an equation sheet, and Q1 or Q2 is the charge. And so D will be the distance between them. And so we'll see this information again later in Gen Chem 1, but basically it tells you this allows us to calculate the charges between here or the repulsion here. So positive energy is attraction, negative energy is repulsion. And so this interaction is really important for bond stability. So later in the semester, we're going to start to put molecules together in such a way that you can basically start to fit them together like Legos. And so we want to be able to calculate, is this a good interaction or a bad interaction? So the next thing we want to think about is, what are we studying? So I like to think about a pot. So if you were to be making pasta water, so we have a pot, and down here we're going to draw some flames because we're cool like that. So the question, or what we want to study, is how long does it take this water to heat? And so down here we have fire, and in our pot we're going to have some water. So the thing is, the system is what we're studying. So in this case, what we're studying is the water in pot. And so in this case, we have this system. And so we can either have an open system. So this would be a pot with no lid. And so that basically means as we heat it up, we're going to have some of the gas molecules escape. However, a closed system, we are going to use a lid. So in this case, we again have our pot. Now we're going to plop a lid on top. We're going to put the same water inside. And we're going to add some fire underneath. And so now this is going to be a closed system, where this other is an open system. And so when we have a closed system, we're actually going to observe that the water will boil faster. In comparison to the open system, because all of the heat energy that we put into this pot is going to stay in the pot. And so a closed system, energy cannot be exchanged into the surroundings. In an open system, energy is freely exchanged into the surroundings. So when we start to talk about in the system, which is what we're studying, and so when it is closed, all of the energy can be contained. When it's open, we're going to basically create a steam bath. And so if our system is the water in the pot, the surroundings is everything else. So in this case, the fire is part of our system, but the heat is going to be exchanged between the system and the surroundings, or any of the energy. So energy is what we're going to start talking about. Energy is considered a capital E. And so the first law of thermodynamics states energy cannot be created nor destroyed. There are several laws of thermodynamics, and so we're only really going to talk about the first one in this chapter. So internal energy is the sum of all energy for a system. the reality is it's really difficult for us to calculate the energy of a given system, but we can calculate the change in energy. So let's think about a practical example. We want to calculate the energy you spend to run 5 miles. So how much energy do you need to run 5 miles? So it's really hard to know how much energy you're spending at mile marker 1. So at mile marker 1, specifically at that instance, how much energy is it? But the way we could calculate this is to look at over 5 miles. You used some value, and we'll mark that as X calories. I have a fitness watch, and so at the end of any fitness activity, it tells me how many calories I've spent. But it's not really accurate in any 1 second or even in 30 seconds. So in order to do this, we calculated the change in calories. So this delta equals change. Now, you may be thinking, Dr. Malcolm, didn't you tell me that delta equals heat? It does when it's in a reaction. In this case, this delta, so the triangle is change or delta, and it tells you that we're going to subtract these two. So the calories burned would have been the calories spent over time, which is the final, minus initial. So anytime we see this delta symbol, we know that it's going to be final minus initial. So it turns out that we can calculate the change in energy. It's just going to be the final minus the initial. Now, the other thing that we need to kind of think about is the fact that I told you we didn't know the energy. So we're going to be able to calculate the energy, but not use E initial or E final. So to calculate delta E, it's going to be Q plus W. So when we think about this, as a reminder, Q equals heat and W equals work, which is also shown down here. And so Q is a calculated value or a known value. It's something we measure, how much heat is transferred. Work you can calculate, so it can be force times distance. So when we think about delta E equals Q plus W, there are a couple of things we want to think about. Delta E has 3 parts. 1, it has a number associated with it. That could be the number 5, the number 300, or just the number 0.21. So that just gives you a finite value. The second value is that it has a sign. And that means it's either positive or negative. And so lastly, we need to think about the units, which would be joules or kilojoules. Nope, or calories. And so we're going to think a lot, mostly about joules and kilojoules. Calories are not often spoken about in this case. And so when we have delta E, or a positive delta E, the system gained energy. If we have a negative delta E, the system lost energy. So it's really important to think about the flip side of both of these. And so that means that the surroundings gained energy. So in all of these cases, the energy goes from the system to the surroundings or the surroundings to the system. It isn't necessarily something that ends up not necessarily nowhere, but just kind of moving around. So when we think about Q plus W and delta E, we can look at this table. So if we have a box where we have a system, so outside of that will be the surroundings. So if we have heat going into the system, which would be this, positive heat in, positive work in. So work is done, heat goes into the system, work is done on the system. Then delta E is also going to be negative. So don't forget that the equation that we're talking about here is delta E equals Q plus W. Now, likely you're saying, adding two things together is relatively simple math, and that is entirely true. The more complicated part of these problems, as we'll see in the next bit, is that we're going to have to assign the signs. So we need to be able to figure out if Q is positive or negative. Also, this is for positive. We'll see it a lot in this chapter. And this equals negative. So we need to figure out if Q is positive or negative, and we need to figure out if W is positive or negative. We can also be asked to calculate whether or not delta E is positive or negative. And so you might be like, this doesn't sound super complicated, but it's all about where our point of reference is. So in this example over here, on the left side, we have a box that talks about the system. Heat goes into the system. But we also need to remember that heat going into the system is heat leaving the surroundings. So we're going to have to use the context clues in the question to try to figure that out. So one of the ways, so heat is relatively easy. The temperature goes up or goes down. Work is much more complicated. So if we think about work like a gas tank. And so positive work is you put the gas in. Because positive work is work done on the system by the surroundings. So you are adding gas into the tank. So negative work means that you've spent gas to drive. And so in this case, negative work is the system does work on the surroundings. So the gas will be spent to drive the car from one place to the other. A lot of times we're going to talk about using a piston. So in this case, you'll see this in the homework system where it'll have a flask and then basically a valve here, which will measure. So you can either push here and then it will increase the pressure in this valve, or this valve will push against the surroundings. So when work is done on the system, it will be pushed down. When work is done by the system, it will push the valve up. So let's look at an example. So in this example, gases A and B are confined within a cylinder and react to form a solid C. As the reaction occurs, the system loses 1,150 joules of heat to the surroundings. The piston moves down as the gases react to form a solid. As the volume of the gas decreases under constant pressure, the surroundings do 480 joules of work on the system. What is the change in internal energy for the system? So we're being asked to calculate delta E equals Q plus W. So the first thing we want to think about is which values correspond to which. So we have the system loses 1,150 joules of heat to the surroundings. And then the other one we're going to look at is the work. And so the surroundings do 480 joules of work on the system. So in this case, when we set up these values, we know that Q and W are what we're looking for. So when we look at the problem, the system loses 1,150 joules. So that means the Q is going to be negative, which is negative 1,150 joules. So the surroundings do 480 joules of work. So that means that work is done on the system. So we have positive 480 joules. So to do our calculation, it's delta E equals negative 1,150 joules plus positive 480 joules. And so when we plug this into our calculator, we should get negative 670 joules is delta E. So the hardest part of this question isn't actually the math. It's that we want to be able to make sure we are assigning the signs in the correct way. So the other thing we kind of want to think about is the fact that delta E is what's called a state function. So the way we know it's a state function, so state functions, are identified by capital letters. So far, delta E is the only state function we've met, but heat and work are both lowercase letters. I know my W's look like an uppercase W, but they are in fact not. So a state function does not depend on the path that was taken for the reaction to occur, just on the difference between two states. So all of that is a really fancy way of saying they are path independent. So it doesn't really matter how you get there. So if we think about the altitude change between New Orleans, which is below sea level, and Denver, which is the mile-high city, the distance between these, the change is the same. No matter how you get there. If you fly, drive, take a train, or anything else. So the distance between those two doesn't matter. Now, things that are path dependent are work and heat. So it matters how much energy or how much heat you're going to spend in order to drive, fly, or take a train, right? And so we can think about that in terms of path independence. So one of the things I like to think about is if person A is here and they want to go here. One way that they could get there is to basically walk here. Or they could go on a trip, they could go see the, 9 wonders of the world and get here. A state function tells us that if we are measuring distance, it is path independent. Basically, the distance between them, the physical distance between where they started and where they ended is the same, whether they walked directly there or they ran all over the place trying to get there. So path independent tells you it doesn't matter. Path dependent tells us that the amount of energy it took you to get there is dependent upon the path.